Hi, I'm Leah Albaugh, and I'm presenting work done with Scott Hudson and Lenning Yao on physically situated tools for exploring a grain space in computational machine knitting. Fundamentally, this is work about how to reason about and support material creativity in computational fabrication. So we've gotten pretty excitingly good at using computationally controlled machines to build us stuff in the real world. These techniques can help us make material objects precisely and flexibly, and critically in qualitatively new ways. Computational materials can have entirely different constraints and tendencies from traditional processes. Another word for constraints and tendencies is grain. The term draws an analogy to the concept of grain in woodworking, where grain is a material property of the wood itself. On a technical level, grain is the specific arrangement of cellulose fibers in the wood, which is a low-level material property. It's arguably best analyzed with a microscope. But for a woodworker, grain is an aggregate material property which affects every stage of how the wood is cut, it's joined, is sanded, and finished, and ideally reasoning about all this stuff is intuitive for an expert. Of course, to get to that level of expertise, woodworkers work in a hands-on way with wood. Computational materials have grains as well. These are manipulations which are easier or harder within a given process, or they're modes which arise out of similarly low-level interactions between algorithms, machine control, raw materials. Opportunities for a tremendous amount of creativity can be found in exploring these grains, but they're often abstract or indirect, or they're mediated by fabrication equipment and on-screen interactions. So, how might a creator find and explore the grain of a computational material? In this work, we propose an approach that we call a grain space. It's a computational space encapsulating a material grain. You could also think of it as a parametric style. It's a set of associated aesthetic guidelines and constraints. And as such, a grain space does not enable every possible material outcome from the broader fabrication method. Rather, it delineates an area for exploration. And in this work in particular, we chose a grain within computational knitting, represented here by a Shimaseki V-bed weft knitting machine like the one we have in the lab. And we chose knitting because it's an exemplary demonstration of the material complexity that can arise from an aggregate of low-level manipulations. As you may know from other works in HCI and adjacent fields on computational knitting, knitting is a way of making a fabric surface out of interlocking loops of yarn. And there are many styles of knitting, from lace knitting that emphasizes patterns of holes, to various kinds of color work knitting that are essentially pixel-like. In this work, we choose a particular grain within knitting that is called brioche knitting. On the slide, you see a swatch of two-color brioche. It's a fluffy fabric, and it's got this cool branching and merging patterning on a contrasting color ground. Here's a representation of how brioche is created on a knitting machine, which uses two rows of hook-shaped needles to produce its fabrics. The two colors of yarn form two interlocked faces of fabric, so here it's white on the side facing us and purple on the other. The fabric is constructed row by row. Each yarn adds new loops to the columns on its own face, and then it tucks to connect to the other face. The rows and columns of loops on a face basically establish a grid, and from there, any loop on the front face of the fabric can stay in its own grid lane, or it can veer right or left, or it can split into two loops and send one to the left and one to the right, or both of them in both directions, or whatever. It's not actually important for you to remember these specifically, but the point is that we define a small set of things loops can do. It's a little alphabet of brioche possibilities. We might visualize these as fairly literal images of loops, or as little tiles. Something that's important to note is while I've highlighted left versus right-leaning stitches with orange or purple, they aren't really pixels. They're really loops and columns that are essentially little vectors. They can leave their own grid cells behind. Under the hood, these are represented as positive, negative, and zero values in an array. And because we maintain a straightforward mapping from those arrays to the actual low-level machine knitting operations needed to produce them, this is a grain space. It is a way to think about possible outcomes within the medium, coupled with a way to do it. Once curated and defined, a grain space forms the basis for reasoning about the design and implementation of tools for exploring material effects. The grain space provides both a manipulable representation between the inputs and outputs, as well as, through its form, an inspiration for the design of heterogeneous tool interactions. So, for example, I said that the brioche atoms are basically little vectors. maybe I just want to get my hands on those vectors, move some arrows around, right? As if I had an instrument for playing brioche knits. So we made this object. It's a board of knobs, and each knob can click into one of three positions, right? Straight up, leftward, or rightward. And it's totally electronically passive. It's just a piece of wood and some plastic knobs. So you can take it wherever, right? You can do some plein air knit design, and then you can take out your phone, you can take a picture of the board, and you can pull it into the mobile web app to be processed. Using a little bit of OpenCV, it'll rectify the image, and it'll produce a brioche pattern. And the ability to really specifically arrange a knit stitch makes it possible to make things like this little ad hoc animation. Each frame here is small, but once we're in brioche space, we can stitch the frames together to make a little film strip. Or more complex manipulations like compositing a brioche swatch into a shaped object template like this hat. Composition rules can be specified in brioche-like terms. For example, you could consider how one loop's lean direction might influence nearby loops in that direction. Zooming out a little bit from the loop-by-loop level, supported by the knob board, what if we had another input tool that starts from this idea that brioche operations are not pixels, that they're kind of a flow line in a visual field? Optical flow is an established idea in computer vision, and we implemented a tool to take in image data, derive gradients of image tone change, convert those to brioche flow, and from there, you can run a simple loop preview visualization, or more fun, you can produce an actual knit. We wrap this in a mobile web application that can be used on phones or tablets. You can take an image with your mobile camera, apply various computer vision manipulations to it, change parameters like the number of stitches in the output swatch, and then send it to be knit. Taking it a step further, what if we did actual flow lines, like based on a genuine computational fluid simulation? In this interface, you again take a picture of something, and then the system treats the edges in the image as barriers in an interactive simulation. You can swirl the fluid, you can step the simulation or pause it, and then you can translate those fluid motion vectors into brioche space, winding up with a pattern that is, in a sense, inspired by the visual input given, but even more chaotically so. This is a weird and fundamentally computational thing to do. It's slipping from a material into an abstract representation, acting on that representation with complex algorithms from another domain entirely. But also, by wrapping these up as mobile web apps, we're putting the interaction focus in the physical world. With the snapshots and fluid interfaces, instead of moving knobs on a board, you're encouraged to go find intriguing textures and capture them into the system. This is a curational process, and the physical world is messy, so you might not be able to find what you had in mind, but conversely, you might find other stuff instead. This is a tension. It was surfaced in a small user study we ran with 6 participants. They were all people with textiles experience and some background in visual art and design. So after we introduced them to and allowed them to play with the snapshots and fluid manipulation interfaces, we discussed their creative practices, both with this tool and in their own personal practice. A topic that came up repeatedly was one of control. One participant found our systems fundamentally frustrating. There was just too much of a gap between that participant's goals and the highly indirect physical input systems that I gave them. However, other users described this as more of a productive frustration, or even a necessary part of creativity. One participant specifically talked about how they use physical materials in their own professional practice because it introduces that little bit of chaos. This participant commented on representational gaps as a source of poetry, saying, from translating from digital to analog, there's always some loss in the process or some translation error or whatever, which I find really inspiring. This breadth of reactions is to be expected. A grain space is not intended to encapsulate an entire medium, and particular creators may have affinities with some spaces more than others. For creative computational materiality to fully flourish, we need to recognize multiplicities in the materials themselves and how creators explore them. In summary, we introduced the concept of a grain space, which is a computational space rooted in a material grain, as an approach to designing creative fabrication tools. We use the example domain of computational knitting to demonstrate how a grain space can inspire and underpin a set of physically based tools, and we discuss the ways these tools can support unique creative practice in that domain. We hope this approach of identifying and representing unique material grains, in tandem with computational spaces for generating and manipulating them, can help you explore the opportunities at the joints between computation and material properties. Thank you for listening. Feel free to reach out to me via email, leah@cmu.edu, or Macedon, Leia at hci.social.